So here we are, week 12, 11-9 through 11-13. It's Monday. We're meeting today. It's an odd week. No school Wednesday. So here we go. We are actually starting chapter 5 next, not chapter 3. And this is just based on what other teachers in the district have decided to do for pacing. And because they've all taught the class before and I have not, I'm going to go with what they think is the next important thing to do, which is probability, which I think is really fun. So hopefully that will work out well. Our resources will be updated after class today, as they typically are. As of right now, it's just a bunch of empty squares, but there is an AP Daily video for what we're going to talk about today. And I do have the pages and such for the textbook of what we're going to cover today, if that is something that you would like to look at. Those are already there. Okay, and then we have our discussion board for today will be based on today's lesson. What are the odds? This has to do with probability. One thing I did want to go over, and I'm going to use this space to kind of review that real quick. There was some issue with uploading pictures into a text entry box for you guys' submissions and the self-assessments. I know some of you guys had issues with that, or some students had issues with that. I do not know if your text editor looks like this. There's 2 possible text editors within Canvas, and it depends on your overall settings. And I don't think that I adjust those for you guys. I think you get to choose that yourself. This one I have set up in mine right. This is the editor that I'm using. So I'll do this one first, then I'll switch it over to the other editor so we can see what that one looks like. And it's going to take a little bit of time out of our lesson, but I think it's important to know how to use the tool so you guys can do what you want. In this version of the editor, which some of you may have enabled and some of you may not, there's different ways to insert images. There's this little icon here where you can upload an image and you have other user images, blah, blah. If you go to upload an image, right, you can drag and drop into this square or just choose an image. Canvas likes .png images to embed or to put into the text editor. That's its favorite form of image. So if you can save your images as .png files, that seems to work best. JPEGs tend to just show up as text sometimes. So if we put it here, it's going to give me a preview, and you'll hit submit. You can put a description, you don't need to. And then it just takes a second, pops it in there. You can resize your image to fit. This one gives us image options. Right, you can custom size it, blah, blah, blah. All right, so that is in this editor. You can input a image that way. You can also use the insert image and get to the same place in this text editor. All right. You can also edit the HTML in here, but I don't see any reason why you guys would need to do that. So then, in your settings, the feature options, I have the rich content editor enhancements enabled. That's what changes the way that the text editor looks. If I turn that off, it should go back to the previous version. Right. So this is the other version of the text editor, which is what, if it didn't look like the one we just saw, then it looks like this. So then, the recommendation is to change your settings to the rich content editor enhancements. you should be able to change to that. So I believe I've seen screenshots of some students' editors that it looks like that new one. And that will give you the easy way to upload an image, and it gives you extra options that are not available in the other editor. So seems like that is why some students are having a major issue putting an image in, because it's not easy in the other editor. Okay, well, hopefully that answers some questions. Definitely answered some questions for me that I didn't realize. So there you go. That was something I wanted to go over because it was an issue within the self-assessment. So yeah, that's our week. I have the Chapter 2 self-assessment that's been published. It's not done yet. It'll be published later. I'm giving 2 weeks as far as like the timeline to try and get this turned in. Obviously, we finished Chapter 2 last week. This is a self-assessment that goes with it. Every chapter will have a self-assessment. So don't feel too rushed on this. It's due 23rd. So no stress on that. We'll have one more discussion board this week, and that'll be it. All right, so then let's get into the meat of it. Let's get into our lesson. Here we go. It is Monday, November 9th, 2020. First, we're going to look at where we have been so far and where we're going next. All right, so far, we've done Chapter 4, Designing Studies. It's covered sampling and surveys, which was, I'm going to go through this relatively quickly so we can get into our actual new lesson. If you need me to slow down, though, please tell me. How to sample, we have convenience sample, voluntary response sample, bias, random sampling, simple random samples, SRS, stratified random sample, cluster sample. We have things come up as undercoverage, non-response, response bias. These are things that could make our sampling not good. We covered in section 4.2 experiments. This was observational studies versus experiments. We have treatments, experimental unit subjects. These are all vocabulary terms within experiments. We looked at how to experiment well. We looked at random assignment, comparison, control, and replication. Those are the 4 parts that we must include in a well-designed experiment. We have to have completely randomized design. Right? That is when you have a random assignment, right? You randomly select your people, and then you randomly assign them to the treatments. That is completely randomized. We looked at things such as placebo effect, double-blind, single-blind, statistically significant. We have block and randomized block design and matched pairs design. And we lastly looked at the scope of inference. Chapter 4 had a lot of things and a lot of new things for most of you. This is just a quick rundown of some of the key vocabulary and ideas that we covered in Chapter 4. And then we went into Chapter 1, exploring data. First, we looked at making sense of data. There's individuals and variables. Individuals are the things being measured, right, or the things that we're collecting data about. Individuals are the things we're collecting data about. Variables are the things being measured. Right, we have categorical variables and quantitative variables, and those, when we look at those numbers, those make up a distribution. Categorical data we can represent with bar graphs, pie charts. We have two-way tables. We have marginal distributions, conditional distributions, and between those things, we hopefully can make an association. Our quantitative data we can represent with dot plots, histograms, stem plots, back-to-back stem plots, split stem plots, split stem plots. We always need to consider shape, center, spread, and outliers. We can use the SOX or CUS letters to remember those things. We can have symmetric or skewed distributions. We can have them be unimodal, bimodal, or multimodal. When we describe quantitative data, we must talk about the center, which we can use the mean or median depending on which is more appropriate, right? Mean is typically more appropriate for symmetric. Median is typically more appropriate for skewed. With that, we can talk about the spread, which is range, IQR, standard deviation, right? IQR for the spread is typically more appropriate for skewed, standard deviation, more appropriate for symmetric. Both Skewed or symmetric. Skewed or symmetric will have a range from the minimum to the maximum. We have identifying outliers using the 1.5 times IQR rule. That is where you take 1.5 times the IQ interquartile range, and then subtract it from the minimum value and add that number to the maximum value, and that gives you a lower bound and an upper bound. Anything outside those bounds are outliers. We have box plots from the 5-number summary: minimum Q1, median Q3, and maximum. We have comparing distributions. One other form of identifying outliers, which we didn't spend much time on, is if a value is more than 2 standard deviations out beyond the mean, right? Less than the mean or greater than the mean. That could be considered an outlier. All right. That's a quick rundown for chapter 1. Chapter 2 is modeling distributions of data. We have describing location in a distribution. We use percentiles, cumulative relative frequency, standardized scores, or z-score. And we looked at transforming data. That was when we add or subtract numbers to our values to shift them, or multiply and divide to create other shifts. We have density curves and normal distributions. The density curve always has an area of 1 under the curve. The mean and median of a density curve are related based on the shape of that curve. Normal distribution, which is symbolized with n, parentheses, mu, sigma. We have mean and standard deviation completely describe a normal curve. We looked at the 68, 95, 99, 7 rule, the standard normal distribution, table A, and making comparisons with z-scores, and then doing calculations. We have normal distribution calculations, finding the proportion of a curve based on a given value, finding a value given a percentile or proportion of a curve. So being able to kind of go back and forth between starting with a value and getting to proportion, or having a proportion and going back to the original value. And then lastly, we looked at assessing normality, right? If something is normal, it's approximately symmetric and bell shaped. It is close to the 68, 95, 99, 7 rule. And we can also use a probability plot to help assess normality. So that's a quick rundown of what we've seen so far. I think it's important to always kind of refresh and remember what we've done so far so we don't forget it. It's not going anywhere. It's still there. We just have to continue moving on. All right. So now, what's next? Probability. Oh my goodness, so exciting. Okay. So here's our introduction. Chance, essentially, is everywhere. Right? We see that with rolling dice, flipping a coin, rock, paper, scissors. Right? These are all things that take chance, right? Playing the lottery, right? Just chance you might win. There's chances everywhere. There's probability to many things, right? Playing slots in a casino, which you guys aren't old enough to do, but you know, you've seen them, right? These are all things of chance, right? You know, other examples of chance is like genetic inheritance, right? There's all these different probabilities of how things are going to match up between, you know, parents and things. Chance also comes into play when we're setting up, designing studies, right? When we randomly assign things and randomly select our population to take part in a study. There's a lot of chance involved, right? There's a chance that we get a poor selection of people or subjects, and our study isn't that good. There's also a chance that we get a really good selection of people, right? And the thing with chance is that in a short, small window, it seems entirely random. But as we do more and more and more repetitions of the same chance thing, patterns usually emerge, So first thing we're going to do is we're going to play a game. I'm going to try to do this here. So what we're going to do is I'm going to put a couple of things in the chat here. All right. So was there? So here's our 1 in 6 wins game. As a special promotion for its 20-ounce bottles of soda, Soft Drink Company printed a message on the inside of each bottle cap. Some of the caps said, "Please try again," while others said, "You're a winner." The company advertised the promotion with the slogan, 1 in 6 wins a prize. The prize is a free 20-ounce bottle of soda, which comes out of the store owner's profits. 7 friends each buy one 20-ounce bottle at a local convenience store. The store clerk is surprised when 3 of them win a prize. The store owner is concerned about losing money from giving away too many free sodas. She wonders if this group of friends is just lucky or if the company's 1 in 6 claim is inaccurate. In this activity, you and your classmates will perform a simulation to help answer this question. For now, let's assume that the company is telling the truth, that every 20-ounce bottle of soda it fills has a 1 in 6 chance of getting a cap that says, "You're a winner." We can model the status of an individual bottle with a 6-sided die. 1 through 5 represent "please try again," and 6 represent "you're a winner." So the only way to win is to roll a 6. All right, you guys are going to roll your die 7 times to imitate the process of the 7 friends buying their sodas. And you're going to just keep track of how many of your rolls are winners. All right, then in the form, you will just type in the number of wins that you had in your 7 rolls of the dice. So roll the dice 7 times, keep track of how many 6s you get. That number of 6s that you got gets entered on the form. Then I'm going to use that form to create a dot plot very quickly. So, all right, here is our results. So, what do you guys notice about these results? Right, just first, right off the bat, what do we see? Mostly zeros, yep. Thank you, Jocelyn. What else? Outliers, yeah. I don't know how someone got 9, because you could only get 7, but that's okay. Most of the data is to the left, yep. So this is skewed to the right. 1 and 2 are the same. Wait. 1 and 2 the same? 1 and 3 looks the same height, but yeah. Let's see, we had 33 trials. Most likely to lose and to win. Yeah, I mean, would they set up one that they're most likely to the company would lose, right? 1 and 3. No, you're good, Matthew. Yeah, right. So yeah, that's definitely skewed. It's skewed to, they would say the house, right? Yeah, 7 and 9 only occurred once, right? 5 only occurred a couple times. 0 to 3 obviously are the most common, right? So let's look at, like, in our our summary statistics here, like the median is at 2, right? So the middle is at 2. The mean is almost in the same place, the 1.9, right? Which is a little odd for this distribution, right? Considering it's skewed to the right, the mean is actually to the left of the median, barely, right? So that's odd. But yeah, so do you think that, oh, that's okay, no worries, Anna. I was wondering how we got a 9, but yeah, that makes sense on the keyboard. They're right next to each other. All right, and that's okay. That's part of collecting data, right? There's possibility of error, and that's why we have these like parameters to find outliers and things that we can exclude from our consideration at times. All right, so does it seem fair for the company to say 1 in 6 wins? What do we think? Does that seem fair? Based on our simulation here of 33 responses, does that seem fair? Or do you think we would need to do more trials to be able to answer that question? In other words, do you think we need more information? Probably do more, yeah. See, they're saying probably do more just in case. Yeah. Because within like a large soda manufacturer, right, like Coca-Cola, do you think it's enough for them to make that statement to only have 33 trials? Do you think they could say that with just that small amount of data? Nah, it's not reasonable, right? They're gonna sell so much more soda than 33 sodas, right? So they need to run larger simulations to get a more accurate idea of what the chances are. Right? So that's where probability comes in. Right, so this brings us to what is probability. I forgot to stagger these. Darn it. I'll fix that in the next one. So this is what we're talking about. An important fact emerges when we watch coin tosses or the results of random sampling and random assignment closely. Chance behavior is unpredictable, just as we saw in our experiment with rolling the dice in the short run, but has a regular and predictable pattern in the long run, meaning the longer we go with these things, the more predictable it becomes, which is when we can say what chances are, what probability is. This is the basis for the idea of probability. Right? Probability describes what happens in very many trials. We must actually observe many outcomes to pin down a probability. You can't make a statement about probability based on 35 samples. It's not enough. The law of large numbers states that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. That means that like flipping a coin, so to say, right? The more times you flip a coin, the closer you're going to get to 50-50, 50% heads, 50% tails. But if you only flip a coin 10 times, you might end up with 7 heads and 3 tails, which doesn't fit the probability. But as we go more and more and more, right, we see that kind of converge to that 50% chance, right? That number, that single value that it starts to converge to over many, many, many repetitions is called the probability. Good. And again, I don't think this slide is going to do what I want it to, but there we go. So what is probability? Here is our textbook definition. The probability of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. So again, probability is typically talked about as a proportion between 0 and 1 and not a percentage. So we can easily convert that to a percent if we wanted. Okay, outcomes that never occur have a probability of 0. An outcome that happens on every repetition has a probability of 1. 0%, 100%. An outcome that happens half the time in a very long series of trials has probability 0.5, such as the chances of flipping a coin and it landing on heads, or landing on tails for that matter. Probability is measured in the decimal representation of percentages from 0 to 1, 0% or 100%. And again, this kind of comes back to that density curve idea where the proportion of the data under the curve has to add up to 1. So we could put all of these observations into a dot plot or a histogram, create a density curve. The area under that curve must be 100%. And the proportion of things that occur, right, of certain outcomes can give us evidence of a probability. And that's what we're looking at now. What questions do you have? If you need more time to write anything down from the side, can you please raise your hand? All right. So then, that's it. I'm going to end the slideshow. All right. And then so now the discussion board for today, right, has to do with just kind of understanding what probability is and what the numbers that we use to describe probability mean. Right, so it's just a couple of questions, a couple of parts in each one, but it's just like, explain what probability 0.61 means within this context. It says the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Right, what does that mean about the typical U.S. adult? What are the chances that they are eating breakfast, right? So it's just kind of answering some questions about what a value of probability means.